Okay, AP Chemistry, we're now on to Lesson 2 in Unit 14. This is Advanced Atomic Structure, and this is also the second part of your final exam. You want to really try to get these lessons done over the break because it is a lot of information. It's really more than we should crowd into a week, and it's going to be the last week of school when you're going to be extremely busy with everything. So please get these done over the break. I should have all of these up by Monday. That would be December the 27th. And I'll have answer videos up, not of everything, not of every question, but of some of the questions, selected questions I'll have up within a day after that. I will have tutoring on Monday through Friday from 10 to 12, except Monday I'm going to have to cut it short to 11, so it'll be 10 to 11. I'll actually make it 9 to 11. The gate will be open over by the Wiener Schnitzel if you want to come in. I will also be sending out an email and a Canvas announcement that there will be some Zoom hours. It's going to rain next week, or for whatever reason you might not be able to make it into school. So I'll be online with Zoom for an hour a day each day next week. Okay, so with that having been said, let's go ahead and get started on Lesson 2. So in Lesson 1, what we dealt with was energy, as energy entered and left an atom, and it had to do with the movement of electrons from in between orbitals. Now we're going to deal with the structure of the orbitals. What do they really look like? So that's the theme of this particular lesson. It's atomic energy levels. So in earlier units, we used the Bohr model of the atom, which contained simple circular energy levels. We called them orbitals, and they were just simply these circles. We acted as though the electrons went around in these circles. We said that they didn't, but we acted as though they did, just because it's a simple model, and it was as complicated a model as you needed to understand what we were trying to teach. You don't use a more complicated model than you need to understand a concept. Otherwise, it just makes the concept confusing. So what we did is we just said the orbitals are these nice circles, and there you can see 6 orbitals around the nucleus of an atom. Now we're going to learn a more advanced model of atomic energy levels in which each orbital is divided into subshells. So, for example, the 6th orbital up there at the top isn't just a single orbital. It's divided into different parts, and we're going to talk about those. So the subshells are labeled S, P, D, F. That doesn't stand for anything in particular, to my knowledge, but I kind of make up some words that it stands for to help you remember them. So the subshells are labeled SPDF and have shapes described by mathematical equations. The SPDF subshells must occur in that order. That's an important point to remember. In each of those orbital levels, 1 through 6, the S must come first, and then the P, and then the D, and then the F. You can't switch that order around. So, for example, the 4th row orbital of the periodic table has 4 subshells, and we're going to simply call them subshells as distinct from the orbitals, and that's 4s, 4p, 4d, and 4f. You can't switch that order around. It has to be in exactly that order. Okay. So the type of orbitals that a row has depends on its row in the periodic table as follows. Well, the first thing you see is that the periodic table has 4 basic sections that we've never looked at before. And it explains a little bit further and you're gaining a little more insight as to why the periodic table is shaped the way it is. Because these subshells, these 4 subshells, occupy 4 very distinct parts of the periodic table. So the first row only has an s orbital. The second row has an s and a p. The third row has an s, a p, and a d. And interestingly, you'll notice that the d orbital for the third row is down in the 4th row. It's not up in the 3rd row. We'll talk about why that is in just a moment. The 4th row actually adds another subshell. That's the s, p, D, and you see the 4f orbital down there on the bottom. Each subsequent orbital also has S, P, D, and F. The 5th does. And actually that's not quite true, because the 6, we can say it has S, P, D, and F. However, the largest element in the universe, uranium, is in the 5f orbital. Therefore, there's really no 6f orbital. In theory there is, but not in the real universe. And then 7 also S, P, D, and F. So each row of the periodic table must fill its subshells in this order, S, P, D, F. Again, emphasizing that point. It has to be in exactly that order. So memorize that order of those letters. So here's the first row. The first row elements, hydrogen and helium, place an electron in the 1s orbital. Up until now, we just called it the first orbital, or the first row, or the first orbital. But now we're calling it the 1s orbital to distinguish it from the other letters. After the first row, all s subshell elements are alkali and alkaline earth metals in the first 2 columns. So you can see the s's are all over there in the 2 columns on the left. The only exception is helium in the very first row. Each row of the periodic table must fill its subshells in the order S, P, D, F. So the second row. The first 2 elements in the second row, which are lithium and beryllium, place 2 electrons in the 2s orbital. Again, each element contributes 1 electron, or adds 1 electron, the first subshell. When the s subshell is filled in the second row, the next 6 elements, which are boron, carbon, nitrogen, oxygen, fluorine, and neon, place electrons in the p subshell, which has a slightly higher energy than the s subshell. So that's the difference between these subshells. The p's are slightly higher than the s's, the d's are slightly higher than the p's, the f's are slightly higher than the d's. They're a little bit higher energy level. Now, one thing I should have said at the beginning, get out a periodic table, whether it's your book or whether you just pull one up on a tab in the background. You should be looking at a periodic table as we do this lesson, okay? You need to be able to identify some of the elements as we go along. Each row of the periodic table must fill its subshells in the order S, P, D, F. So the third row. The sodium and magnesium electrons go in the 3s subshell. That's where sodium and magnesium are. Aluminum, silicon, phosphorus, sulfur, chlorine, and argon place electrons in the 3p subshell over there on the right. Next comes the third orbital D subshell. Since the 3p subshell must come before the 3d, the 3d is placed in the 4th row. So let's stop and think about that for a second. If the 3d orbital were up actually in the 3rd row, then as you went across the 3rd row, you go from 3s to 3d to 3p. But that violates the rule that we've been saying at the beginning of each of these slides. The order must be S, P, D. It cannot be S, D, P. Therefore, where are you going to put that 3rd orbital, that d orbital for the 3rd row? It goes down in the 4th row, because at that point that cannot be the 4d orbital. Why? Because you have 4s and 4p is over there on the right side of the 4th row. You can't go through 4d before you get to 4p. 4p has to come first. So that's called the 3d orbital because it has to belong to a row that has already had its p orbital. Again, the order has to be S, P, D. So the 3rd row has had its s orbital, it's had its p orbital over there on the right, and now it's ready for its d orbital. So as strange as it sounds, the 3d orbital goes in the 4th row because it must come after the p orbital. All right. We're going to talk about this more later. We'll keep reinforcing this point later on. So D subshells, transition metals, are always placed 1 row below their row number. So the 3D is in the 4th row, the 4D is in the 5th row, the 5D is in the 6th row, and so on. And that D orbital belongs to the transition metals, that valley in the middle of the periodic table. Okay, each row of the periodic table must fill its subshells in the order S, P, D, F. So here's the fourth row. It starts with the 4s orbital, and that's potassium and calcium. Electrons go in the s subshell. Again, have a periodic table. Be looking at that so you know the elements where they are. Okay, then gallium, germanium, arsenic, selenium, bromine, and krypton are over there in the 4p. Next comes the fourth orbital D subshell, and that's down one row below, as we just said. That's going to be in the fifth row, and that's the 4D. And then in addition to that, the fourth orbital has an F subshell. The fourth orbital has an F subshell placed in the sixth row. The periodic table breaks out the 4F, called the lanthanide series, down below. And there's a very practical reason for doing that. If you put the 4F up there where the arrow is coming from, right after where you see 5D, then it would stretch the periodic table out so it was too wide for a single 8.5 by 11 piece of paper. Those last two rows down there would be stretched way out, whereas the ones up above would be just as you see them on this sheet. So that they could fit the periodic table on a single piece of paper. And since it was a natural break to have those F orbitals down there that are separate from the S, P, and D orbitals, they decided to just go ahead and put them down at the bottom of the periodic table and draw arrows toward them like that. So the 4F subshell is 2 rows below the 4th row. You'll notice that the 4F starts in the 6th row and the 5F starts in the 7th row. So the F orbitals are 2 rows below their normal row number. So the 4F subshell is 2 rows below the 4th row. It appears in the 6th row. Okay, each row of the periodic table must fill its subshells in the order S, P, D, F. So the 5th row starts with the 5s, that would be rubidium and strontium. The next 6 elements are over there in the 5p on the right. Then next comes the 5th orbital 5d subshell placed in the 6th row, 1 row below its row number. And finally, the 5th orbital has a 5f subshell placed in the 7th row, called the actinide series, so the F orbital goes 2 rows below its row number. It's in the 7th row. So the 5F subshell is placed in the 7th row. Subshells have unusual shapes that were determined mathematically by physicist Erwin Schrödinger from his equation, which is known as Schrdingers Equation. All you need to know about Schrodinger's equation is that the shapes of the subshells indicate the probability that an electron will be found in a particular location. So if you look at that, that's an s orbital down below that you see there. The electron is most likely to be found where the blue is the darkest and least likely to be found where the blue is the lightest. So very near the nucleus, which is at the center of those axes, is where the electron is most likely to be found. Yet electrons are never found in the nucleus, but they can be found very close to the nucleus. So Schrodinger's electron density distribution of a hydrogen electron, and that's pronounced psi squared, is called the wave function. The wave function gives the probability that an electron will be in a specific location. The darker blue means higher probability. The shapes of the subshells are shown in the following slides. So here is the S subshell. The S subshell is spherical, so it's not circles as we had portrayed it before, like planets orbiting the sun. It's actually a sphere. It's a three-dimensional sphere. It's a ball, basically, shaped like a ball. The diagram on the right shows the 1s, 2s, and 3s subshells. All 3 are spherical. In the 2s and 3s subshells, there are lighter and darker regions. The lighter areas are called nodes. Nodes are locations where electrons are less likely to be found. The 2s orbital has 2 areas of high electron density separated by a node. So you see that there's the central dark area, and then there's a darker band outside of that. But in between those two, there's a node where there's a lower probability of finding an electron. Why is this? Why does the electrons like to be either close to the nucleus or in that outer circle, but not in between the two? That's what Schrodinger's equation says. That's all you need to understand. You don't need to understand the equation or the reasoning behind this. So sometimes it's important to know what you don't need to know. You don't need to understand that. Just understand that those lighter areas mean there's less chance of an electron being there. The 3s orbital has 3 areas of high electron density. You can see those in the diagram. And it's separated by 2 nodes. One node is a little bit darker than the other, but nonetheless it's considered a node. Alright, so again, that's all you have to understand. The darker areas are the higher probabilities of electron density, and the lighter areas are the lower probability of electron density. That's all you need to know about Schrodinger's equation. Now we're going to look at the p orbitals. So this is the p subshell, I should say subshell. And the mnemonic is potato, because they kind of sort of look like potatoes. Not really, but they kind of do, but potato starts with a P. So just remember the P subshell is the potato subshell. So let's take a look at those. You have a 3-dimensional axis with X, Y, and Z. Z is almost any book that you look at will be the up and down axes. Which one is the X and which one is the Y? The Y is basically on a flat plane. If you think of it as being on your tabletop, it would be the X and Y axes. Which one is the X and which one is the Y is different depending on what book you read. It's not really important as long as you're consistent. But again, generally Z is the up and down, coming out of your tabletop and down below your tabletop, and X and Y are flat on top of your tabletop. That's the way you should view that. So the px orbital, so we're now, first we broke the orbitals that we used to think of as simple circles into S, P, D, and F. Now we're going to take the p orbital and break it further down into X, Y, and Z. So the px orbital is an orbital that runs along the x-axis there. The py orbital runs along the y-axis, and the pz orbital runs along the z-axis. Okay, now those two potatoes, those potato-shaped objects are called lobes. And you'll notice that the px orbital has 2 of them. That is not 2 different orbitals. That is a single orbital called the px orbital. It just happens to exist on opposite sides of the nucleus. Again, you're thinking that the nucleus is right there in the center of those 3 axes. Same with the py orbital. That is a single orbital, the py. It just has 2 different parts to it, 2 different lobes. One on the right side of the x-axis, one on the left side of the x-axis. And again, those are the probability that an electron will be found inside, is high that an electron will be found inside of one of those lobes. And then the Z, the same thing. Again, the lobes are not separate orbitals. The X has 2 lobes, that's a single orbital, the px orbital. The Y has 2 lobes, that's a single orbital, the py. And the Z has 2 lobes, that's a single orbital, the pz. So the p subshell is further broken into 3 sections. We're going to refer to those as sections: px, py, and pz. Each of the 3 sections is divided into 2 lobes. Lobes are the potato shapes. In between the blue lobes are nodes where electrons do not reside, or at least there's a very small probability of finding an electron outside of those blue areas. So each p section, px, py, and pz, is aligned along an axis. The p subshells in the 3rd, 4th, and later orbitals have identical shapes to the 2p. The difference is they're farther out from the nucleus. As you get to higher orbitals, 2nd, 3rd, 4th, 5th, as the orbitals go up, the subshells are further away from the nucleus. And then again, over on the right, you see the composite. That's really, they're all put together into the same atom. So you see them sticking up in all 3 of those directions, and they're all put together over there on the right. So each of the elements in the pink square contribute 1 electron to the p subshell. For example, the second row contains boron, carbon, nitrogen, oxygen, fluorine, and neon. Each element adds 1 electron for a total of 6 electrons. The electrons are added in the following order. Now, this might be a little harder to understand here, but you'll see it later on. It'll make more sense. First, boron would put an electron in the 2px1. The second electron would go into the 2py1. The third electron will go into the 2pz1. Then you start pairing up the electrons. The fourth electron will go into the 2px2, back where the first electron went. The second electron, the fifth electron rather, will go into the 2py2. That's where the second electron went. And finally, the last electron will go into the 2pz2. That's where the third electron went. So they start pairing up after the third electron. Okay, so that area over there that we've seen before, that's where the p electrons are. It's a slightly higher energy level than the s electrons, even though it has the same row number. 2s, 2p have the same row number, but the p electrons are a little bit higher energy than the s electrons. This order will become clear later in the lesson. It will. We'll see diagrams that will help you to understand this order. So, how many electrons can fluorine hold, and where are they located? So, fluorine has an atomic number of 9, so it has 9 electrons in its natural state when it's not ionized. The first 2 electrons fill the first orbital. Okay, we know that. The second 2 electrons fill the 2s orbital. And then the final 5 electrons fill the 2p orbital in this order: 2px1, 2py1, 2pz1, then 2px2, then 2py2. So if you look at that, the px orbital is the blue. So one of them goes into that orbital. Then the py orbital is the red. The next one goes into that orbital, the py orbital, the red one. Then the pz orbital is the gray. One of the electrons goes into that orbital. Now we go back to the px orbital. The fourth electron goes into the px orbital, and it's the second electron, so we call it px2. Again, that's the blue. And then finally the last electron, the fifth one, goes into the red orbital. That's the py, and that goes into that one. And then that's all the electrons. So another electron does not go into the pz orbital. So that's how the electrons would be distributed. Now, it may appear that each lobe receives 1 electron, but this is not correct. It just, in this example, kind of looks like that. All we know is that the 2px subshell, for example, has 2 electrons somewhere. So both of those electrons could be over to the left side in that blue orbital over to the left. They could both be over to the right in that blue orbital over to the right. All we know is that if there are 2 electrons in the px orbital, that they're going to be somewhere in that blue area. We don't know if they're both to the left, both to the right, or one on each side. So they could be in the same lobe or different lobes. Now we're going to look at the D subshell, and we're going to give that the mnemonic donut. You'll see why when you see the shape right there. The D orbital has 5 subshells. One of them looks like it has a donut, the one in the middle. So we're going to call that the donut orbital. So D is next. Each subshell can hold 2 electrons for a total of up to 10 electrons in the D orbital. So there's 5 parts to the D orbital. You should know these by name, and we'll talk about that. But you can see that each of those parts of the orbital, each of those sections, has 4 lobes, except the one in the middle has 3 lobes. And so that means you clearly can't have an electron for every lobe. It's just not the way it's done. It just means somewhere in each of those different sections you have 2 electrons, or up to 2 electrons, depending on the element. So the dxy, the dxz, and the dyz are pointed in between these axes. So there's 4 lobes, for example, for the dxy, and it's pointed. You can see it up in the upper right. those 4 lobes are pointed in between the x and the y axes. Not right along them, but in between them. The DXZ, that's the one down on the lower left. And it has 4 lobes, and they're pointed in between the x and the z axes. And finally, the DYZ, that's the one on the upper left. Those 4 are pointed in between the y and the z axes. The DZ squared, or DZ2, it shouldn't be called squared, is oriented along the z-axis with the donut intersecting the x and y axes. So there you see that. It has 2 lobes, one up, one down, and then a third lobe, that's the donut that goes around it. And that's the DZ2 orbital. Finally, the dx squared minus y squared, it looks like x squared minus y squared, orbital has lobes pointed along the x and y axes. You can see that there. So you should know these names and understand that for the d orbital. And so those are the 5. So each of those different sections can hold up to 2 electrons. So that's a total of 10 electrons that can be held in the d orbital. So the d orbitals represent electrons added by the transition metals. So if you count each row of transition metals, that's the yellow, you'll see that there's 10 elements there. Each of those contributes an electron. That's a total of 10 electrons. Okay, so only s and p orbital electrons can be valence electrons. D orbital electrons are never valence electrons. So remember, the valence electrons are the ones that do the chemical bonding, and it's only the s and p electrons that do that. So let's say you're talking about the element cobalt. It's in the 3d orbital. That means its electrons are in the 3d are further out than any of the s or p electrons. So can't they be valence electrons if they're the furthest out? And the answer is, and you don't need to be able to explain this, you just need to understand it, is that d orbital electrons are not ever valence electrons. Only s and p are valence electrons. Notice again that for s and p there's 8 of them, and that forms the octet rule. So you don't form chemical bonds with d level electrons other than metallic bonds, but not covalent or ionic bonds. Okay, now we're going to talk about the d subshell, and we addressed this question, why is the 3d subshell in the 4th row? But let's do it one more time to be sure it's clear. Remember that subshells must be in the following order: S, P, D, and F. The D subshell represents the transition metals, and the first one we encounter is in the 4th row. If it were referred to as the 4D subshell, then the order of the 4th row subshells would be 4S, 4D, where you see yellow 3D, it would be 4D, 4P. This violates the order of SPD. Since the 3rd row has already had its 3s and 3p subshells earlier in the previous row, then this d subshell must belong to the 3rd row, not the 4th row. So illegal is to call it 4s, 4d, 4p. Again, even though it's in the 4th row, it's not called the 4d orbital. That's illegal. SDP is illegal. Down below, legal is to call it 4s, 3d, 4p. That's the proper order orbital. Okay, F subshell. The mnemonic, far too many subshells. I couldn't think of anything better. But the F subshell has got 7 subshells. And you can see they have a lot of lobes. So the F orbital has 7 sections. Actually, 7 sections, I should have said. Each section can hold 2 electrons. So even though each of those sections has a whole lot of lobes to it, 6, 8, quite a few, each one can only hold 2 electrons. Again, those simply show, those lobes show the probability that an electron will be in those areas, but each of those sections can only hold up to 2 electrons. So that's a total of 14 electrons found in the F orbital. You do not need to remember the names or exact shapes of the F orbitals. That's just too much information. As with the d orbital, F orbital electrons cannot be valence electrons. Only s and p orbital or subshell electrons can be valence electrons. The f orbital represents the elements in the lanthanide and actinide series elements at the bottom of the periodic table, down there. So, textbooks disagree on where the 4f and 5f orbitals begin, believe it or not. So you see in that diagram, let's just take the sixth row. You have the two 6s elements there. Then you have the 5d, the first of the 5d subshell. And then you go to the 4f. So according to your textbook, it's different. The 4f subshell begins immediately after the 6s subshell. This would make element 57, lanthanum, and again you should be looking at your periodic table, the first element in the 4f subshell. So your textbook says that the F rows go where that arrow is pointed, where it says here, in between the S subshell and the very beginning of the D subshells there. According to other textbooks and the diagram below, the 4F subshell begins after the first element in the 5D subshell. So you see that you have the first element in the 5D subshell, and then you have the 4F subshell. Down below you have the 6D, the first element in the 6D subshell, and then you have the 5F. This would make element 58, cerium, the first element in the 4F subshell. So who's right? Where does it go? The answer is, who cares? If textbooks can't agree, you won't be responsible. Your textbook, again, is the one that says it goes, the F orbitals go before the D orbitals. They go right after the S. So the 6X, and then you start right away the 4F, and then when you're done with 4F, you start the 5D. In the next row down, it's 7S, and then right after 7S is done, you put the 5F in there, and then when you're done with the 5F, then you go back to the 6D. That's what your textbook says. Other respected textbooks say what this says. It doesn't really matter. Just kind of understand where they are. Electron configuration is a notation for the orbitals and subshells that the electrons of an element occupy. The order that electrons fill energy levels can be determined by reading the periodic table like a book, from left to right and from top to bottom. This produces the following ordering of subshells. And there you see it there. So 1s, 2s, kind of what we've done. 2p, 3s, 3p, and then 4s, and then from 4s you go to 3d, and then to 4p, and then 5s. Anyway, you can see all those right there. So we're going to do this diagrammatically here in just a moment. The energy levels are ordered in a bottom to top structure called the Aufbau structure. So there it is. So again, it looks a little confusing. They seem kind of jumbled around, but if you simply read the periodic table from left to right, top to bottom, you'll get that order. So let's start with this. There's 1s right there, first row. Then the first two columns of the second row are 2s. So we're going left to right in the second row, and then 2p. Then next we go down to the next row, just like we're reading a book. It's 3s, and then 3p. And there you see the different sections in the p orbitals as well. So each one of those lines there can hold 2 electrons. We'll see that in a moment. Now we go down to the next row, it's 4s. And then before you go to 4p, you have to go to 3d. There's the 3d. So you just go read it as you see it in the periodic table. There's 3d in a little bit here. Okay, then there's 4p. Now we go down to the 5th row and we have 5s. Then we have 4d. And then we have 5p. And then 6s. And now, before we get to the 5d, we're gonna do it the way your book does it. Then the 4f is fitted in between there. So this diagram is not showing that. This diagram is showing it comes after the 5d. Again, we said who cares. We're going to say here though that it comes right after the 6s. Okay? So sections on the same energy level are referred to as degenerate energy levels. For example, 3px, 3py, 3pz are degenerate energy levels of each other. The word sounds bad. The word degenerate sounds like it's a bad word, like there's something negative about it. It's not. In chemistry, degenerate just means same energy level. That's all it means. It has no negative meaning or connotation to it, okay? So there you go. So anything that's on exactly the same level are called degenerate energy levels. Okay, so 3 rules determine how electrons are placed in the Aufbau structure. The first is the Aufbau principle, that electrons fill the lowest energy level first. So the 1s is going to be completely filled before we go to 2s. 2s is going to be completely filled before we go to 2px, 2py, 2pz. Those 3 different sections are going to be completely filled before we go to 3s, and so on. Hund's rule. Hund's rule states that electrons of the same spin, up and down arrows, you're going to see what up and down arrows means in a second, are placed in degenerate subshells and spread out before those with opposite signs. You'll see what that means in a minute. Finally, Pauli exclusion, 2 electrons cannot have the same 4 quantum numbers, but what that means to us is that you can't have 2 up arrows in the same section or 2 down arrows in the same section. One has to be up, one has to be down. So let's just get into viewing that. Okay, so there's the first electron. It's placed in the 1s orbital. The second electron is going to place there rather than the 2s because we want to fill the lower energy level first. That's the Aufbau principle. So we put the second arrow there, but it's pointed down. That's the Pauli exclusion principle. You can't have 2 up arrows in the same section or 2 down arrows in the same section. So we've now filled the 1s. What does that mean, really, that up and down? It means they have physically opposite spins. Remember, electrons are both negative. They want to push apart from each other. They want to repel each other. However, if they have opposite spins, if they're spinning in opposite direction, that somewhat offsets that negative repulsion so that they can live together. They can manage to live together in the same section. If they had the same spin, then they're going to really repel each other and they won't be able to stay together in the same section. That's really what that means, and that's all you need to understand. It's actually called the spin of the electron. Okay, now Aufbau says the next electron, this would be beryllium. The third one, by the way, would be, lithium, would be lithium. Again, look at your periodic table as we go along. It's going to be right there. It's going to be the first electron in the 2s. Now we have to fill the 2s before we go to the 2p because the 2p is at a higher energy level. So we're going to fill it with an opposite spin electron pointing down. So now we filled the 1s and 2s. So now we're up to beryllium, element number 4 electrons. Now we're going to go up to the 2p orbital. And we put the first one as an up arrow there. Now the question is the second electron going to be a down arrow in the 2px or an up arrow in the 2py? The answer is it's going to be an up arrow in the 2py. That's Hund's rule. It says you want to space out those electrons first before you start putting them together. Do you remember way back in September when we were learning how to diagram an atom and we had the circular orbitals, and I had you spread the electrons out, one on the bottom, one on the left, one on the top, one on the right? That's what's happening here. The electrons want to spread out as much as they can until there's no more space, and then they have to start pairing up. So the next electron is going to be an up spin in the 2pz. Now the remaining electrons have to pair up. So you put the fourth one in the 2px pointing down, the fifth one in the 2py pointing down, and the final one in the 2pz pointing down. So now we have the electron configuration of neon, the end of the second row. That's the noble gas at the end of the second row. One thing you'll discover is that after the 1s orbital, everything from then on, when you get to the end of a p orbital, you've put in all the electrons in a p orbital, you're at a noble gas. You're at the end of a row. So we're now at the end of the second row at neon. Now we're going down to sodium, 3s. There's an up arrow. And then the next one is going to be magnesium, a down arrow. So we filled up the 3s. Now we're ready to go up to 3p, and it's done exactly the same way as 2p, px, py, pz. Now we go back opposite spins, start filling those downspin, downspin, downspin. Now again, we're at the end of a p orbital, so that's the end of the third row, and that's argon. That's the electron configuration of argon. Now we're going down to the fourth row, and that's potassium right there, and calcium right there. Now we're going into the transition metals. We're finally hit the transition metals. That first row of transition metals in the middle of the periodic table. The way the electrons position themselves is similar. Up, 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 and now this last one we're going to learn an exception, but I'm not going to teach it to you right now. Let's just keep it simple, and let me just say that the next electron is going to go there. Okay, you're going to learn that that's not correct later on, but let's just learn it in the same way, in the same order here. Okay, now we go back and we start pairing them up. Down, 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 down. Now where you are is you're at the configuration of zinc. That's the last element in the transition metals in the fourth row. The 3D transition, 3D subshell, but it's the transition metals in the fourth row. That's where you are. You're not at the end of the entire row of the periodic table. You're just at the end of the transition metals. Now we go to the 4p, x, y, z, and then downward spin x, y, z. Now we are at the end of a p orbital, which means that we're at the end of the fourth row, and that's going to be krypton. Now we go to 5s, and that's rubidium, and then strontium, and now the 4d, and I don't even remember what all these are down there, but there they are, up, 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 and then we start pairing up, down, 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 and we're at the end of the second row of transition metals, and that is cadmium, CD on your periodic table. Now we're going to finish out the fifth row. We're going to 5p, up, 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 down, 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 and that's going to be xenon. So you're now at the end of the fifth row, and that's the noble gas configuration for the noble gas, xenon. And finally we go to 6s, we fill that, and now we're ready. Before we go to 5d, we're ready to go to 4f, okay? And that's what we talked about. We're going to say that that begins right after the 6s orbital. You start with the 4f. Now it can hold 14 electrons because there's 14 elements if you count them in those f rows down at the bottom of the periodic table. So up, 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 up. Notice I didn't give them their formal names there. I just called it 4f1, 4f2, 4f3. You don't need to know those names. It's too much information. And then we do down, 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 and we have 14 electrons in the 4f orbital, and that's as far as we're going to take this. So again, just learn that order, understand how you place them, and that's all you need to know for this. Okay, now we're going to learn how to write something called an electron configuration. It's telling you, it's basically a sentence that explains what we just drew. So here we go. Watch this and watch down below where it says electron configuration. So let me explain what that means. Elect config is electron configuration. Elect config means condensed electron configuration. You're going to see how that's much shorter than electron configuration. So watch what we do. The first electron goes in the 1s, just as we did on the previous slide. That's referred to as the 1s superscript 1. It's not to the first power. It's not a math equation. It's just 1s. I will sometimes call it first or second or squared or something, but it's really not that. It's not a math equation. So what it means is in the 1s orbital, you have one electron. Now, what if we add a second electron? That would be helium, right? So we're going to take that away. We're going to put the second electron in the 1s. So the 1s is now filled. So that's called 1s2. So that's the electron configuration for helium is 1s2. It's just said 1s2. Okay, now we're going to add another electron. That's going to go in the 2s orbital. And by the way, there's the electron configuration for helium. You're going to see why I'm putting that down there as we go on here. Okay, now we put a third electron in. It's in the 2s orbital. That would be lithium. So there it is. That's the electron configuration for lithium. It's 1s2, 2s1. Now we're going to put a second electron in the 2s. That would be beryllium. There it is. And now it's 1s2, 2s2. That's the electron configuration for beryllium. Now we're ready to go up to the p. And we don't, there's the first electron goes in the 2px orbital. So that's 2p1. We don't call it 2px1. We don't make the distinction in electron configuration between x, y, and z. It's just the 2p orbital. It's saying there's one electron in the 2p orbital. Now we go to the next one. It's going to be 2py. So now it's going to be 2p2. So the entire electron configuration, that by the way would be carbon, would be 1s2, 2s2, 2p2. That's the way you would read that. It's starting to get longer and longer. Okay? Now we're going to put the third electron in. That would be nitrogen. You put it right there. Now you have 1s2, 2s2, 2p3. And so it continues. The fourth electron is going to go there back in the 2px. That's going to be oxygen. So that's going to be 1s2, 2s2, 2p4. Fifth electron in the p orbital, 2p5. And finally, the noble gas neon, there's the sixth electron in the p orbital, is 2p6. So that's the electron configuration for neon. 1s2, 2s2, 2p6. So what we can now do is we can summarize that electron configuration as being the electron configuration for neon. Okay, that's going to be part of the condensed electron configuration in just a minute. That's why we're doing that. Let's keep going. There's the first electron in the 3s orbital, so that becomes 3s1. There's the second in the 3s, that becomes 3s2. There's the third, it goes into the 3px, so that's 3p1. So that's the electron configuration for aluminum. Okay, that would be 1s2, 2s2, 2p6, 3s2, 3p1. You have to say the whole thing to state the electron configuration for aluminum. You can see it's starting to get longer and longer. Now we put in the next one. That's going to be 3p2. The next one is 3p3. The next one is 3p4. The next one is 3p5. And finally, the last one in the p orbital is 3p6. So we're at the end of a p orbital. So that means we're now at the next noble gas, and that's going to be argon. There it is. So that's the electron configuration for argon. Now we go up to 4s. Everything we have before, but now you add 4s1, another electron, 4s2. Now we're ready to do the 3d orbital. Okay, and there's going to be 10 electrons there. So I'll do those a little faster. The first one is 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, and finally 3d10. Okay, so now we're at the end of the first row of transition metals, and that's the electron configuration for zinc, which is the last element in the fourth row transition metals, the 3d orbital, in other words. Okay, now we keep going, and you can see this electron configuration is getting longer and longer. So there's 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. That means we're at the end of a p orbital. That means we're at our next noble gas, which is krypton. So you can take that entire long electron configuration and just put in square brackets Kr. Boom. That Kr represents all of that electron configuration that you see above. Now we're going to continue 5s1 and 5s2 right there. Now we go to the 4d orbital, and there's 10 of those, so I'm going to move through those very quickly. And you can see it's 4d3, 4d4, 4d5, 4d6, 4d7, 4d8, 4d9, and 4d10. So that puts us at the end of the 5th row transition metals. That would be cadmium, Cd, on the periodic table. Now we're ready for the 5p subshell. So here we go. Oh, there's the 4d10 down there at the bottom. So here we go with 5p, 5p1, 5p2, 5p3, 5p4, 5p5, and 5p6. Again, we're at the end of a p subshell. That means we're at the next noble gas, and that's going to be xenon. So that entire long electron configuration is the electron configuration for xenon. And we're going to go on and just finish with 6s1, 6s2 electron configuration. It's just the way they chose to do it. Okay, they do it in number order, but here we do it by SPDF order. Okay, now the condensed electron configuration. Now that you've seen that big long string up there for the electron configuration, here's what we do. Okay, we do the same thing we did before. Just happen to put this on a different slide, so I'm going to speed through it. It's exactly what we just did before, and we're doing it for potassium. So potassium is the first element in the 4s orbital. So there it is right there. So there it is. There's the electron configuration of potassium. But remember what we said? We said everything through that 3p6 represents a noble gas, and that's argon. So what we can do is the condensed electron configuration is simply to put the abbreviation for argon, AR, in the square brackets, and then write the 4s1 after it, and bam, you're done. That's the condensed electron configuration. So anywhere you have a noble gas, you simply write that noble gas's abbreviation in square brackets, and then you only have to write all the 4sps, 4ss's, for all that after that noble gas. So here, instead of writing everything from 1s2 up to 3p6, we just wrote AR in square brackets because that's what that electron configuration is. And then we added the 4s1 for potassium that came after the AR. So that's the condensed electron configuration. Okay, write the electron configuration and condensed electron configuration for the potassium ion. So remember from ionization rules that potassium is an alkali metal. It's in the first column. It likes to lose an electron, so it can be like the nearest noble gas. Do you remember that? You have to go back to the ionic bonds in the foundations unit way back about lesson 7 or 8. That's where we would talk about that. Or just go to your charge number by ions or your 60 common ions, and you'll see that potassium ionizes to a 1+. So watch what we do here. We're going to add all of our electrons the way we did before. I'll do it very quickly. And there's potassium right there, just like we did on the previous slide. So what it says we do down below is you start with K, potassium, and remove one electron. This produces the electron configuration of the nearest noble gas, argon. So watch up above. We're going to take that electron away from 4s because it's ionized. And now what we have is just the electron configuration of argon down there below. Remember, elements want to ionize to be like the nearest noble gas, and for potassium, that is argon. So there it is. That's the electron configuration for the potassium 1+ ion. It's simply the same electron configuration of argon. Two elements can have the same electron configuration if one of them is an ion and one of them is not an ion. Then in this case, potassium 1+ ion and argon have the same electron configuration. It's what you see right there. Okay, now we're going to get into a little bit of an exception, and it corrects something I just told you a minute ago. So filled and half-filled subshells are more stable than other configurations. This results in some exceptions to the order we have just seen in the d orbitals. So you're going to see it's just a couple of little exceptions, but you want to remember them. They could test you on this because they figure if you understand this, you understand all the more basic stuff. So here's the question: what is the electron configuration of chromium? So look up chromium on your periodic table. and you'll see it's number 24. It's the fourth element over in the transition metals of the fourth row, or the sixth element over total. Okay, and there's chromium. So find chromium. So it's the fourth element over. So let's look at how chromium would be formed. Here we go. Okay, and I'm going to do this kind of quickly because I think you understand the concept of building up there by now. If you don't, go back and watch what we just did. So now we're at the end of the second row, and there it is right there. Now we're going to go on to the third row. And now we're going to fill the p orbital in the third row. And now we're at a noble gas right there. That noble gas would be argon right there. Okay, now we're going up to down to the fourth row, 4s, potassium, calcium. And now here we go. 1, 2, 3, 4 is chromium. So there it is. It's got 2 electrons in the 4s orbital and 4 in the 3d orbital. But what we just said is that chromium would be more stable if it could have a half-filled d orbital. So what are we going to do? It's got all of its electrons. Where do you get any more electrons from? You can't just add electrons. That's what chromium has. It has that number. So watch what happens. Watch the 4s line over there. Put a box around it. We're going to take that electron away from the 4s, and we're going to put it, look over at the 3dz2 over there on the right. We're going to put it in there. Now chromium has a half-filled 3d orbital. How did it do it without changing the number of electrons? It just borrowed one from the 4s. So chromium is actually more stable in that configuration than it is in the original configuration that we would have figured it should be. So let's read down below. It says, since chromium will be more stable if it has a half-filled 4s and 3d orbital, the 3d orbital will borrow an electron from the 4s. So that's actually the electron configuration of chromium. You should know this exception because they could test you on it. Very, very likely test you on it. Very possibly test you on it, okay? Now, we said more stable when it's half-filled or filled. So let's see an example of the filled. And there, by the way, down at the bottom, I just added it in, is the electron configuration and condensed electron configuration. So it's 4s1, 3d5 is what would come there at the end. Okay, so let's look at the same thing for copper, okay? This is a case where it's going to be more stable if it has a filled d orbital. So let's go ahead and let's start plotting the electron configuration for copper, and here we go. We'll do that quickly here. Okay, they were at the 4s, now we're at the 3d xy. We're filling up the 3d orbital, and now we're going all the way over, and there's copper right there. It's the second to last element in the fourth row transition metals. Comes just before zinc. So that's the way we would have plotted copper. That's the way we would think it should be. But the same rule applies. So let's read down at the bottom. Since copper will be more stable if it has a filled 3d orbital, the 3d orbital will borrow an electron from the 4s. So again, watch the 4s line over there on the left. We're going to take that electron, we're going to take it away, and we're going to go ahead and put it over here, and we're going to put it there. So now copper has a filled 3d orbital. And so if we look down at the electron configuration, it's going to be 4s1 because there's only one electron in the 4s orbital, 3d10. Alright, so those are the exceptions that you should understand. It's when you can either half fill or totally fill a d orbital, then that situation will occur. Alright, and that does it for this rather long lesson. Again, this is really 2 lessons packed into one. You'll find, though, that the problem set goes fairly quickly if you understand this. Just follow this. And this is the second part of your final exam. Big incentive to get it done during the holiday week. If you turn it in on Monday, January the 3rd, you get 10% extra credit for both the assignments and for the exam. If you don't get it done in this week, we're going to do these lessons in the last week. And if you wait until then to do them, you're going to have big issues, okay? It's not going to go well. Get them done this week. That means you won't have these lessons to do in the last week. You won't have any lessons to do in the last week other than just doing some reviewing and doing some class projects, okay? So we'll see you on part 3 of the final exam and on day 86, the second to last day of the semester. We'll see you on the next lesson.